Okay, thank you, Mr. Chairman. My name is Laila Inandrasana, yes. And this work has been done in co-author with Nathan Seles, who's my former PhD student, and with his colleagues from the Central Transportation Facility in Grenoble. And my talk will be about a mix of experimental measurements with stress field theory. The motivation is here, so in the framework of the evolution of microstructure at the local scale, at the microscopic scales, and linking this to the mechanical properties. And about mechanical properties, we're talking about stress or strain. So let's have a look what we are doing. Measurement, for instance, at macroscopic scale. The strain will be obtained from the process displacement and or for the strain gauge. And the stress is obtained by the load divided by the net section. Whereas at the microscopic scale, we can calculate or determine the strain tensor with DIC or DVC. Substrate, for example, that's about stress. We can't access to the local stress unless you have a model. So this is, the goal is to find out the signature of the stress fields at the microscopic scale. The basic idea comes from the idea of Rice and Tracy in 1969 that void growth is linked to the stress reactivity ratio. So here you see that it's something to do with stress. Okay, so to do this, we have the outline of my talk will be first I will talk briefly about theory, because we have to stick with the stress field theory. Then I'll talk about the experimental measurements of the void inside this polymeric material. And then I will talk briefly about the finite element analysis, where we have we will go to the principal stresses components, and then finish with the result discussion and the conclusion. So first of all, the material or the engineering structure which is involved in this study is dealing with plastic pipes, which is loaded with internal pressure for a long time, and the durability, long-term durability, that's failure at 50 years, for instance, is obtained in this map at this location. For that, we have this map of the time versus the applied stress, and to do this, we have to pressurize here with the monotonic increasing load, in this case is static loading, and then we have to reach this domain where there is a concept of transition time. The same thing is, the same map have been drawn for load parameters in fracture mechanics, for instance, and as you can see, we have to reach this. And I would say, all of these load parameters, such as the toughness of the K1, J1, and the J integral, has been discussed in this conference, but there's a few. I have not seen some presentation about the system integral. But here, I won't stick on the system integral, but we just know that this C star is the parameter to control the singularity, the stress singularity, like for HRF field. We'll talk about this. And what is important also is here is the transition time. So we need in the experimental data to reach this transition time in order to have this stabilized secondary group. So let's start with the Bridgman theory for finite notch radius, drawn by here. And at the beginning, the hypothesis of Bridgman is to say the strain tensor here in the net section is homogeneous. So there's no gradient of all strains. And also that the radial strain and the hoop strain are equal. And from this, you derived the stress gradient. The maximum stress is here, and as you can see, that there is a gradient of stress. The maximum is located in the center of the specimen. You can see also that due to this hypothesis that the hoop stress and the radial stress are equal. Okay, so in opposition of this, for the stress field of fracture mechanics, nonlinear fracture mechanics, you know that the stress singularity and the singularity is on the notch root, not in the center. And you can see here the theory, but I have put here some red stars, meaning that we have, this is dependent on, this parameter is dependent on the plane strain or plane stress condition. And it's supposed that for flat specimen, it's supposed that at the lateral surface you have a plane stress condition, whereas at the plane mid-thickness, you have a plane strain condition. Meaning that for 3D specimen, you don't have a continuous evolution of the stress singularity, for instance, because you have just at the lateral surface or at the mid-thickness. So these things have to be checked also. There have been some modification about the HRR field here. The first one is already discussed in this conference. For instance, that due to blunting of the crack tip, the maximum stress here is lower than the singularity. And also, the location of the maximum stress is depending on the hardening exponent. Now, when doing this, we also, if you can plot, if we plot here also the strain singularity and the stress singularity, you can see that this happens on the stress gradient, but not on the strain. This is a very interesting result for the comparison that we have to do later. Okay. Now, the second modification is about the time singularity, because if you have time-dependent nonlinear behavior, if you, at the crack, at the fixed distance of the crack tip, theoretically, you have this stress relaxation. And if you reach this secondary, the transition time for secondary grip here, you have here the Riedel and Surprise theory giving you back the stress singularity, also modified by the Rice and Johnson modification. But all of this modification can be taken into account by the finite element calculation. Okay, so about the experimental part, I show you here the PA6, the semi-crystalline polymer. We have a spherolytic microstructure here. The voiding of this material has been explained in this paper with Nathan Celes, that the voiding is inside this sphere. It's the kind of grain size for the polymeric material. And then we have the nucleation. We have observed with the nanotomographic data. We have seen the nucleation of voids inside the spheroid. The size of spheroid is about 5 micrometers, so we have this characteristic length for the material. We have machined 3 specimens. The first one is here in T4, notch inside, but we tested 4 millimeters of notch radius initially here to see the Bridgman theory. Then we reduced the notch radius here. We have here 0.45 millimeter of notch radius in order to see what happens for which radius the Bridgman theory is then transformed into fractal mechanics theory of the stress field. And then we have also done grid test on a CT specimen. The thickness is 2 millimeters because we have just this is the possibility to do the observation inside the tomograph. So the data at the macroscopic scale is, I would say, current data. This is the COD, the crack opening displacement, and the crack opening displacement rate. Tests have been stopped here at this point in order to take the specimen, the deformed specimen, and observe what happened at the synchrotron. Okay? Now, these deformed specimens have been observed, and we are sticking with this three, would say, volume of interest. So this is called the tomographic volume of interest, which we are deal only with the radial description of the variables here. And to process the data, we need to obtain what we call the statistical volume of interest here, which is something like a cube. The size is about 50 micrometer, which means that there is about 100 spherulites inside, so more than 100 voids. From this SVOI, we can compute or calculate the void volume fraction, because we have to, we can count the volume, the sum of the volume of voids inside, which are the black pixel here, and divided by this SVOI. And as in this material, the void has a shape, a cylindrical shape. So we have the diameter, in fact, two diameters, phi r and phi theta. This is the radial diameter and also the hoop diameter in this coordinates, cylindrical coordinates. And we can also calculate the average height of these voids inside the SVOI. So these are the result of this experimental measure. So you can see here, for instance, all of these black dots are voids. And you can see the notch here, there's no void there, no damage. And then we are going to the central part of the deformed microstructure. You can see that the void is increasing in height, in volumes. So you can deliver this curve where the void volume fraction is plotted against the normalized radius from here to here. So you can see here that the void volume fraction is maximum in the center of the specimen. We have measured also the average height and the average diameter. So we have these data which are available. Please note that here there is something which is pairing, and this difference between the diameter in the sense of the radial diameter here and the hoop diameter is different. This means that the void is not, the base is not circular but elliptical, with the minor and the major axes that are measured, and also the void height has been listed here. What happens for the NT0.5? So here is the data set from the tomography. This is a measurement, there's a contour map, which we can see here the size of the SVOI, and we can map here, this is a experimental measurement. And then if you plot them here, the void volume fraction against the normalized radius here, we can see that the maximum is near the notch here, but not at the center, like here on this notch radius. We have also measured the void diameters and the void height here. And then for the CT specimen, we have two directions. The first one is through the width, so in the crack propagation here, direction here, void volume fraction is like this, so you can see that at the mean thickness, you know that the maximum void is at a certain distance, which is about 200 micrometers from the crack tip. We have also measured the void diameters in the two directions and the void height. The same thing has been obtained through the thickness. See, here at the location of the maximum void volume fraction, that is 2000 micrometers, right? And you can see the distribution of the void volume fraction through the thickness. And the same thing for the void height and void diameter. How we then compare this? So, if you talk about the finite element analysis, the meshes have been done like this, and what's important is that we didn't need to do we have just fixed a mesh size of about 50 micrometers, which is with the SBY side, because what we have observed is within this volume. Then the model is a modified GTM level in order to take into account the hardening of the polymeric material and also to take the time-dependent deformation. Here we have measured this initial volume fraction here. And then there is something which is specific for this for the optimization of coefficient, because we have used inverse method, of course, because we have a structure. And then we have used this the optimization method by using statistical data at the macroscopic scale. We can see here for the obtained set of coefficients. Here the macroscopic variables that are in good agreement, but also we used the distribution of the void volume fraction, because we have in the model the porosity. To have this, we can see here, for instance, the total map of this porosity, maximum in the center for the NT4, maximum here for the NT045, and for CT specimen, we can see here the necking in the thickness, so thickness reduced thickness here, and the maximum void volume fraction is at mid thickness and also at a distance, small distance from the notion radius. So once we have these coefficients, we have now to compare with the fields of the diameter or the height of voids. So, in opposition to what is done currently for the finite element analysis, which uses unit cell in order to follow the shape of the voids, here we just compare directly the stress components, to the void height and void diameter. So this is the control matter of the damage. So we ensure that we have the maximum void volume fraction inside. Here is the diameter. So this is in the second y-axis we have the stress. So here the stress, radial stress and hoop stress. And you can see here that there's a difference as obtained here, even if it's not so different here on the stress, but it has not the same scale here of the stress, because you are just to correlate the profile of this. For the height, it's pretty well. It works pretty well with the observed height of the voids. The same thing for NT045. Have the same data here for the stress and the sticky well. Here, the difference is due only to the fact that there was stress relaxation in the specimen, and there was also some stressing because the observation had been done months after the experiments. And now for CT specimen, which is interesting, we can see here, for instance, the maximum principal stress, so Rice and Johnson, and it sits well with the similarity here with the void height, and also the void, the diameter. And the same thing has been obtained, so we have here a continuous evolution of the stress or the void refraction through the thickness for CT specimen. Okay, so I arrive on my conclusion. The conclusion remark is that from tomography and laminography, you may have through thickness and 3D evolution of the microstructure. Then this can be extended in order to have to assess the model, finite element model. And the main conclusion is that void shapes evolution has been correlated with the evolution of the principal stress components. The outlooks, future work, will be based on to see the stress relaxation at the crack tip, but more than next week I will have this conference in Milano for the mechanics of time-dependent materials. We have also this addresses to his fellow Jacques Besson. We can have here an experimental measurement of the load parameter in 3D by using this data. And we are now to develop, in fact, the anisotropic damage we have initiated in this paper by Caro et al. Thank you for your attention.